Hi again, this is Ms. Granucci. I'm here to give you a tutorial on Excel. In this video, what I want to show you is how to graph in Excel. We are definitely going to use graphing in Excel, especially in physics, because we like to look at the relationships of the data. For example, if we're going to do a study of motion, we're going to want to know what's the relationship between time and distance. Is it a 1-to-1 ratio? If I go 5 meters, does it take me 5 seconds? And then the next second, does it take me 6 seconds to go 6 meters? Or 60, I don't remember what I said. But anyway, point being is, is it a 1-to-1 relationship? Is it a 1-to-2 relationship? Is it a 1 to 1 and squared relationship, an inverse squares? So it's actually incredibly important to use graphing as a way to visualize the relationships of our data. Excel is a very powerful program we're going to use to kind of explore those ideas. So what I'm going to do is show you how to generate a graph in Excel. It's not as, a lot of people get scared by it. It's not too bad. I'll show you how to do it. And then how to make a trend line to identify the relationship we're looking at. I'm going to show you how to adjust things in Excel. Sometimes you might have to change the scaling and the increments, which is actually not straightforward. And then I'm going to show you how to analyze the data, in terms of error analysis. So just, is it a good set of data, bad set of data? How well does relationships, look, etc. in Excel? So let's go ahead and open our Excel file. I'm going to use the same file that I used before. And here's our data set. So from the previous video, we kind of used this data and made it up to show you how to do calculations, analyze data, etc. So what we're going to do is we're actually going to be plotting some of this information. So to generate a graph, first of all, if you notice this dotted line, if you go to page layout and go to grid lines print, what's going to do is going to give you where the page ends. So naturally I want to put the graph over here so it's not, on a page where, on the end of the page where it gets cut off. I will take off points if your graphs get cut off, just because not because I'm trying to be mean, but if I'm looking at a set of data, I shouldn't need 2 pages to look at it. So just, be cognizant of the page, where it's going to go. If you need to move things around, you could do that. So let's go ahead and add our graph. So to add a graph, you're going to click on an empty cell just so you're not adding it over here, because if I put it right here, the graph will go right there. So it doesn't matter where you put it. I'm just going to put it right here. Now, initially what people want to do is highlight things, and actually that's the you want to actually do it the opposite way, which instead of highlighting it and asking it to graph, you want to tell it what to graph. So what I'm going to do is, let's say we want to graph, I'm just going to put what we're graphing up here just so you know. We're going to graph distance on the y and time, average time, on the x. So say that's the request here. And I'm just putting it there just so you know what I'm doing and why, for that point. So we're going to go to Insert. And then depending on what yours Excel looks like, it's probably very similar. But what you want to do is you're going to look for the one that looks like this. It's called a scatter plot. So I'm going to put that right there. Now you want a scatter plot because it specifically plots your data to find a mathematical relationship. You don't want a line graph. Line graphs are used for time series data, so like how does the population change in 2001 and 2002, etc., like that. Like that's what it's mostly for. You definitely don't want to use bar graphs. Those are for histograms and counts, which we won't do here. Maybe in biology, but we're not doing counts here. We want scatter. And we want the scatter with just the data. We just want points here. So we don't want anything else. So I'm just going to move this over so clearly that it's, not on our data, and just make it big. It's blank because we didn't add any data. That's okay. So here's what you're going to do. So there's 2 ways to do this. You can either right click and click select data. It's going to tell, we're going to tell it what data we want, or we go to the button that says select data. So it's asking you, what is your data source? So we have to add our data. So skip this step. We're going to add our data. So first of all, series name just gives you a title of the series. So this could be like what it is. So this could be ball on ramp. What's the title of the data? What does it represent? Then it says, what's your x? So specifically, I said x is the average time. So I'm going to highlight the average. So notice that as soon as I do that, it goes up here, although I don't want it there, but that's fine for now. So I'm going to put this over here so you can see what I'm doing. So X values, I want to highlight the time, the average time trials. So I'm going to highlight those. I'm not going to highlight the title, and I don't have letters in here because then the graph gets messed up. So you have to have just numbers, which is why we're going to put the data, the units up here. So as soon as I click that, I'm going to click the button. So I'm just going to show you again. I'm going to click this button, and then I'm going to highlight it. I just replicated the same thing, and then click the button again. So that's the X. The Y, I'm going to click this button, and I'm going to select the Y values, which is the distance. And there you have it. It's pretty simple. And you press OK, and you press OK. So that's my ball on a ramp. So right now, it doesn't know how you want it to look, so you have to tell it what to look like. So if you go to Quick Chart Layouts, the best way to do this is I'm going to ask you for pretty much this one all the time, which is a function on R squared value, axis titles, etc. like that. So, oops, Quick Chart Layouts, click on that. And there you go. So this will represent the average time trials in seconds. And this will represent the distance in centimeters. Just like that. Okay. Now, ball and ramp is not an acceptable title because what you want, just like you did with the title right here, you want it very descriptive. What are we looking at? It's okay to have it as a sentence. So this is the distance and time trials of a ball on a ramp. So a lot of times what students will do, this is usually a speed lab, is write speed of the ball. So that's incorrect. Even though we might use this to find the speed, the data right here doesn't show anything about the speed. So do not put your what you're looking for as the title. You want to put what's actually there. So obviously it's time and distance here. That's what you want to put. So putting the speed of the ball is incorrect. So what we have here is a official title. We have axes labeled appropriately with units. That's what I'll be looking for. And the right scaling. So you can get fancy with this. Let's pretend for whatever reason, by the way, that the trend line's not there. Okay. I'm going to ask you for a trend line because it tells me how it's an estimate of your data in terms of a line. How does it fit a straight line? So what you could do to do that is if you click on the data points, if you right click in the data points, one of the data points, so it could be any of these. So notice if I don't click it, it's not going to work. You have to click on the data point, add trend line. And in this case, I want it to be linear. So I'm going to click on the linear option. And I'm just going to move this out of my way for a second. And then I'm going to ask you to display the equation on the chart and this thing called R squared. I'm always going to ask you to do this. Then you could exit out of that, and then you can move this. I would ask you to move this out of the way so that we can see it. So that's how you add a trend line. And let's just say that you want to, I'll move this back here. Edit the increments. So if you right click onto here, you can go to Format Access, and they already do it for you, but you can actually set it. So maybe you want to do it. Let's say the major, we're going to do it by tens instead, and then the minor could be by fives. So you can change the axis to stretch it out a little bit. So tens might be too big. Actually, maybe we can even try 1. And you can see that's too much going on at the bottom there. So you can play around with this. I actually agree with the program, as 5 seems to be pretty good. Same thing on this side. If you right click and go format access, you can change the information there. This is going by 20. If you make it by 15, you could do it by that. I think I again agree with this with it like that. So that's pretty good. So you can go, crazy with the tick marks. You can go crazy with labels and numbers. You can play with this on your own. I'm not going to go into it in too much detail. What you could do too is if you go to format grid lines, what you could do is you could actually change, in fact, if you go to design, let's see. Yeah, if you go to design and add chart element, you can actually change the grid lines. So notice that we don't have any vertical ones. I'm going to add vertical ones here. And that can change really pretty much everything, where everything is, your error bars, where you want your data, your trend line. So there's lots of things there, but usually this is what I like. So it turns out that in physics that the slope of your graphs actually have a physical representation. As a kind of quick thing, if I do distance and I divide it by time, by definition, it doesn't like the equal sign, of course. It's trying to, that's speed. So what I might have you do is ask you what the slope of the graph is. So if you remember what slope is from your math class, the equation of line is y equals mx plus b, where m is the slope and b is your intercept. So if I look at this right here, my slope is going to be the 4.7803, which is going to be our speed in centimeters per second, because our measurement for our y is centimeters and our measurement for x is seconds. So I might ask you for slope. The intercept just tells me where it crosses the y, so notice it would cross about 5 right here. If you want to get into more details, that's the initial point, but I usually won't ask you for this part right here. But right before the x is your slope. So that's an important measurement, which is why I ask you to have the equation of the line right there. Now, the other thing that I'm going to ask you is the r-squared value. R-squared is not a part of an equation. It's just how well your data actually matches your trend line. The closer you are to 1, the better your data. So if we have an r-squared of 0.9876, so that's pretty good. It means that most of the data lies on the line, which is, pretty good. So I'm going to show you some bad data just so you see what the r-squared looks like. So what I'm going to do to simplify things is just copy this right here. I'm going to paste it right here. And what I'm going to do is just, I'm actually going to do, what should I do to make this bad data? Take this data set and make this really bad. Okay, so this data literally makes no sense. So what I'm going to do is actually, select the data. I'm going to edit and just do my y's of this one and my x's. Okay. So sorry, I'm just trying to make the data really bad. Okay, so what you can see now is that the r-squared has changed substantially in this one. And notice that none of these data points lie in this line at all. We get a relationship of 0.55, 0.52. So what this tells us is that this does not make a straight line, and that in fact that the data points don't really line up onto our trend line right here. I'm sorry, I read the wrong number. The r squared is 0.2 right here. So it's even worse, which is exactly what an r squared of bad data, well, not bad data, just data that's not related looks like. So that's why I'm going to ask you to always put the r squared on there, because I want to see how close you are to the data. What's really cool in physics is we'll see relationships as r squared of 1. So let me show you what an r squared of 1 looks like, just to show you the major difference here. There you go. R squared of 1 has a very predictable data set, which means that essentially that I know that if I wanted to predict the next number in the series, for example, at 60 centimeters, I know that time is going to be 6. There's no question. That's what r squared of 1 means. Up here, we can see that our r squared is 0.98. So what that basically says is that the next point, if I wanted to say what is the time for the 110, I can make a pretty good prediction that it's going to be a little higher than 20. And that's what this represents, is how well you can make that data prediction. So in this case, it's pretty good, but not as solid as this. And then if I just redo the data as before with the really bad data set, notice that if I get to 60 here, my prediction is I can't predict that very accurately. So that's what this r squared represents, and this is why we're going to use it in physics. So it's a very useful way to analyze our data. I would say 90% of our graphs are going to be very much like this, just going to be one line. So then what does it mean to graph 2? Say I want to graph this data too because I just want to compare it. So I'm going to go ahead and actually make this a really nice graph because I want it to be nice. Why not? Okay. So say there's this set of data, and just to make it different, I'm going to make this outline. Let's make it a nice bright. Let's make it red. So you could do that, and if you right click on the data point, so it should come up format data series. So I had to actually hit the point, so it's hard actually. There it is, format data series. So see how that did that? I can go to the marker, and I'm going to fill it to red instead, so it's different. So I'm going to move my picture again. The color solid. Oh yeah, it's red. It's just weird. I want it to be red. Color red. Okay. So now it's, oops, that's okay. It's all red. Everything's red, including the line. Okay, say I want to put the two plots together. I'm going to make a new graph right now. The easiest way, I mean, you could start over, but the easiest way is just to take this graph, maybe put this over here. And if I want to add another trend line to this, I go to select data. So right click, select data. I'm going to add, I'm going to add the data that's over here. So my x values, if I click on this, my x is my times, my y's is my distance. Press, and this one, let's say if the other one was a ball, let's say this was a cart. Make it cart on ramp. So it's a different object, right? So I press OK. And let's go over here. And then you can see that this is the new data set. I'm going to add trend line, linear, and I'm going to add the equation on r squared. And there you go. So rule of thumb is you can put the trend lines. Usually what I do is I follow whatever is on the legend right here. So blue is first, then the ramp. So this one will go underneath. So blue, so this is the ball, this is the cart, okay? So this would be change ball and ramp, ball and cart, sorry, on ramp, just like that. And then what we can do is we can actually, by doing this, we can compare things quite nicely. First of all, what we'll learn is that the steeper the slope, the faster the object. So we can immediately see that the ramp, the cart actually have a faster speed than the ball. We can actually see that with the slope of the lines. If you notice that 10 right here is bigger than about 5. So clearly the cart went faster than the ball on the ramp. What else we could say about this, which is actually kind of cool, even though I made up the data, is that the cart had a more a more predictable motion on the ramp than the ball. It seems that no matter what we did in terms of the the car, how far it went, it always had a consistent time, where the ball had a less consistent time on the ramp. Which could be is that the ramp, since the cart was fixed on the ramp, it didn't have a chance to maybe roll sideways, which a ball might do. It may not roll completely linear down the cart, down the ramp. I'm sorry. So just by looking at this data and putting the two together, we can compare them, and then we can offer an explanation of why we see what we see, which is what I was just doing. The ball may not go completely linear, which might be why the data is all over. Well, not all over the place, but it's certainly not a perfect line like the cart was. So there's value in that. And then we could look at the R-squareds. Both of them show a really solid relationship between the distance and the time, which means they're predictable. The closer the R-square is to 1, the more predictable the relationship is. And then, of course, we would probably be proving that in lab somehow, saying that the speed is related to the distance over time, and we see that that's true. And then which one has a constant speed? So clearly the orange one, the cart one, has a more consistent measurement, which means it has a better constant speed. Although this has a constant speed, is not as predictable as this. So there's a lot of error analysis you can do with this, which is very valuable in physics. So, oops, I'm moving all over the place here. So as always, I'm going to ask you probably to print these off. So once again, use the grid lines to do that. And then, put them in a row, which is fine. And then if I ask you to print, just note that if you select the graph and then do File Print, it will only select that graph. So this might be helpful. You might want to do this, but notice that there's no other data on this. It doesn't have the graphs or the data table. So if you select on an empty cell and then press Print, you'll find that there's your data. And if you click through the pages, it shows all of the information there. So as always, do a print preview. Make sure you're not cutting off everything. If you need to move things around, you can. And there you go. Okay. So in conclusion, you can make a graph of anything. The way you're going to do that is you're going to click on an empty cell. You're always going to insert a scatter plot with no dots. To add data, you're going to right click and select data. And then you're going to highlight your data according to what and how you're going to graph your relationships. Make sure that you always have it on a separate piece of paper. Well, it doesn't have to be a separate piece of paper. It just can't be cut off by the grid line. So always go to Page Layout and select the Print button so you can see where the page ends. And always File Print Preview, etc. Save it the same way. This just happens to be the same data right here. You could always copy paste this onto a Word document if you'd like to do that too. That's fine. You may have to do that. And then, yeah, you can always add a trend line. It's usually a linear trend line, but you can add a trend line. You're always going to be adding your equation and your R-squared value for analysis. As always, if you have any questions or if you need any more help, you can email me at ngranucci@sacredhearthamden.org for more help with that. All right, I hope this video was helpful, and I hope that you have a nice day, and this concludes our video.